So hello everyone, welcome back to the another lecture. So my name is Ashish and today we will talk about the concept of soft switching in the any converter. Okay, so now we have seen so many things about the DAB converter so far. So now we wanted to understand how the soft switching happen in the DAB converter, right? So for that, initially we'll try to understand the concept of soft switching, how the soft switching happen in any converter. Okay, what are the different methods to achieve the soft switching? And we know that our DAB converter is nothing but the H-bridges kind of structure. So we will try to understand how the soft switching happen in the H-bridge converter. In which particular switch, if we are running our converter, how exactly the soft switching happen in any part of the converter. So we'll just try to understand the few basic things from this lecture. And once we understood the basic things, that we can apply to the DAB converter then. Okay. So this is very fundamental video, but I'm pretty much sure that if you understand how the soft switching happen in the H-bridge converter, I don't need to mention anything when I'm going to discuss the DAB converter soft switching, because now you know after watching this video that okay, this is how the exactly the soft switching happen. Okay, but for that you need to understand this lecture very well. So I'm trying to explain everything in detail. You just try to note it down the things and try to understand the concept from very begin. Okay, so let's get started with this lecture. So okay, here we are in another window. Now we will try to understand the concept of soft switching and hard switching first. Okay, so before moving to the soft switching concept, we should understand what is the hard switching. What is the meaning of hard switching, that we should understand first. So let us say I have one very basic circuit, like my DC supplies, they are connected to one resistive load, and this load will be connected to the circuit through one switch. When switch is on, my circuit is completed. When switch is off, my circuit is not completed, so the current will not flow through the entire circuit. Okay, so very basic circuit I'm going to take for you. Now we need to understand how the switching happen in this particular switch. Okay, so that is the main part we need to understand. Now we know that when it is the ideal case, when switch is on, what is in ideal case? When switch is on, the voltage across the switch will be 0. Okay, and when switch is off, voltage across the switch will have some finite value. Another thing, when switch is on, current flowing through the switch is some finite value, and when switching off, current flowing through the circuit is basically not 0 value, because circuit is not completed. How the current will going to be flow? Okay, what I am expecting is, like when I am going to give any pulse to my switch, what should happen? When I apply the switch, when I apply the gate pulse at this particular instant, my current should have basically start flowing through the circuit, and at the same time my voltage should be fall. Okay, and this is the instant where my transition is happening, right? My voltage is going to be 0 because switch is on. That means my basically current is going to, my current is start flowing, and switch is on. That means the voltage across the switch is 0. So voltage is 0 and some current will start flowing. So it should have some value which is needed to be flow. Okay, and this is the instant where we need to see how my switching is happen. In ideal case, this is fine. It is going to this particular state in very 0 time, and my voltage transition is happen from some particular finite value to 0 in very fast time. Okay, but when we go for some practical case, this transition are not those fast. It will take some time, and then it will reach some steady value. Here also it will basically take some time, and then it will reach the 0 value. So this is how actually happen in the practical world. Okay, so I hope so far so now you understood that okay, when I am going to turn on my switch, what is this voltage? This is the basically gate pulse I am going to give my switch, and this is the current flowing through my switch, and this is the voltage across my switch. What is this voltage? It is a drain to source voltage of my switch, and this is the ID current which is going to be flow through my circuit. Okay, now let us take some off instant value. So this is the one particular graph I have shown you. What is this graph? So you can see that my current is going to be 0 and my voltage is now going to be some finite value. So what is this instant? It is an off instant, because my current is going to be 0 and my voltage across the switches have some value. So it is a off instant. Now I told you that it will take some finite value to go its basically steady state value, right? So there is an overlap between voltage and current. So you can see that there is an overlap between the voltage and current, and this reason you can see that this reason where my non-zero voltage is there and non-zero current is there. So this is the reason where non-zero voltage is there and non-zero current is there. Now because of non-zero voltage and non-zero current, there is a losses V into I. There is a losses into the system, and these losses are responsible for my switching losses, and these losses we called as basically switching losses. And this is how my switch is turned on with the some losses, and this concept we call as a hard switching concept. Okay, this is called as hard switching because my voltage and current have some non-zero transition phase coming, and because of this there is a losses across the switch, and because of these losses we call this as a hard switching concept. Okay, now okay, we understood that okay, there is a non-zero phase will come, non-zero transition of voltage and current is there, and because of that overlapping time there is a losses in the system, and this is called as a hard switching. Now how to reduce that? So let us take the first case. So how to reduce the losses to make the system soft switch. Now what is the meaning of the soft switch? If I will anyhow make this losses equals to 0 or near be equals to 0. So how to make that we will see. So if anyhow I will make the losses like this overlap if I will reduce to 0, then definitely losses will be 0. So by using some sort of mechanism, if I will able to make this transition, this overlapping 0, then I will make it as a soft switching. Okay, so this is the fundamental concept of soft switching. So we understood that what is hard switching, how the losses are happen because of the transition. Now in order to make this basically transition or this overlapping to 0, what we will do some mechanism. Because of this losses across the switch will be 0, and that concept is called as a soft switching. Now how to achieve the soft switching, that we will try to understand. So how to reduce the losses to make the system soft switch? So during the turn on event, if somehow we ensure that voltage falls to 0 before current start rising, then that on duration of the overall transition period can be avoided. So you can see that. So when my switch is on, so we know that when switch is on, my voltage is going to be 0 and current will start rising. So what we wanted to do, somehow what we will do, I will make my voltage to 0 before current start rising. If I will make my voltage to 0 before current start rising, then I can have the overlap duration of 0. This basically overlap is 0, and I can achieve the soft switching, and that we call as the 0 voltage switching turn on. What we are going to call it as 0 voltage switching turn on. Second thing, during the turn up event, if somehow we can ensure that current goes to 0 before voltage start rising, then TSW off, that is off duration period, overlap period can be avoided. So what I wanted to say, when my switch is going to be off, so what will happen when switch is going to be off? My current is going to be 0 and my voltage across the switch will start building up, right? So if somehow I will make the current fall to 0 before my voltage to be rise, then I can avoid that overlapping period, and that concept we called as a basically 0 current switching off state. Okay, so 0 current switching, and this is usually happen during the turn off instant of the switch. And 0 voltage switching, when we have seen 0 voltage switching is basically there during the turn on event of the switch. So this is how actually we can go for soft switching. So there are the very basic fundamental thing. Either I need to make my voltage fall 0 before current rise, that is a 0 voltage switching on, or second, during the turn up event I will make my current to 0 before my switch voltage basically start rising, then it is called as a 0 current switching off state. Now we understood that okay, so these are the two possibilities using which we can basically try to avoid that overlapping, and we can achieve the soft switching. Now how to get the soft switching? Now what are the ways we can achieve the soft switching? So there are the two methods. One is using the external circuits. So using external circuit, like in my circuit I will add some sort of resonating element that will try to make and create such a scenario for me, like 0 voltage switching and 0 current switching scenario, or it will happen naturally because of the operation of the converter. Second thing is what? Naturally happen because of the operation of the converter. In a DAB converter, it is happen naturally. So in a DAB converter, 0 voltage switching happen naturally, and that we are going to understand in detail. But initially we should understand that how in using some external circuit, how we can achieve the soft switching, and then we will see how because of the operation of the converter we can achieve the soft switching. So one more point I wanted to say, that I told you that okay, in our DAB converter, naturally because of operation of the converter, soft switching is happen. So in a DAB converter, zero voltage switching will happen. What I am going to say, zero voltage switching turn on will happen in the DAB converter. During the turn off, it is not possible to have soft switching, but zero voltage switching during the turn on will happen in the DAB converter. How exactly it will happen and all that we will see. Now first thing, we will try to understand using some external circuit how I am going to achieve the soft switching. Now let us say I have my buck converter. If I will add some resonating circuit in it, like my CR, LR and diode, okay, so these three components are added in the buck converter, CR, LR and diode. And if I will add this circuit, so I can have soft switching in the buck converter as well. By default, buck converter, boost converter are the hard switch converter, okay. But if I will add such sort of resonating circuit in it, then I can make the buck converter as a soft switching converter. Similarly, there is a boost converter. You can see that by adding the LR, CR and one diode, I can make the boost converter as well a soft switch converter. Now how to find out the values of LR, CR and how we can tune this circuit, that is beyond the scope of this lecture, but I just wanted to tell you that okay, using addition of some external circuits, external resonating element LR, CR, we can make our circuit basically soft switch circuit. This is the another area of the research, but as of now our main focus is to how the naturally because of operation of the converter we can achieve the soft switching, okay. How exactly by adding this LRCR, how we are going to achieve the soft switching, maybe in future videos we might try to understand this concept as well, but as of now this is beyond the scope of the this particular playlist, okay. Now comes the naturally because of operation of the converter. That part is going to be really interesting. You will understand how exactly naturally in any circuit soft switching will happen or not, okay. So just focus on this particular portion really well and try to understand what I'm going to say, okay. Then you will understand. If you understand this particular discussion, then a DAB converter soft switching is really easy for you, because I'm not going to repeat everything in detail in DAB converter, because here I'm going to explain everything in detail, how basically happen soft switching, turn on soft switching in a DAB, basically in H-bridge kind of structure, okay. So for that, let us take one buck converter example. So in previously we have told you that okay, in one basically to have the soft switching in the buck converter, we can add this particular element, and there only one switch is there. Now what I wanted is that this is a asynchronous buck converter. I will make it as a synchronous buck converter. So what is synchronous buck converter? Another diode is replaced by another switch, okay. So I have now both the switches available with me. Now what I am going to do is that I have modeled the switches in exact way, like the switch is there, its body diode is there, and this is a CDS, and drain to source capacitance is available with the switch, okay. That is a by default it is available. And another switch also I have tried to model it as basically S2, D2 and basically C2, which is my drain to source capacitance of this particular switch. Now can you see that this is a H-bridge kind of structure, right? And such a sort of structure is there in our DAB converter as well. Now there is my LCR. So this L will try to have, what is the function here? I am assuming here is that the current flowing through this inductor is almost will going to be produced as a constant, and I am going to replace it with some I naught value, which is my constant magnitude value, okay. So now this is looks like our DAB converter. It is a one half bridge of the DAB converter, you can say. So and basically current is constant. Now basically current constant meaning basically it will not change its sudden direction, some sort of, okay. So now keep now with this circuit we will try to understand and go in detail like how the soft switching happen, whether at the top switch soft switching is happen or not, whether at the bottom switch soft switching happen or not, whether ZVS happen or ZCS happen, what is going to be happen, all these things we are going to understand one by one, okay. So now take this particular case and we will try to understand the few concepts. Now I am going to take the case number 1 when S1 is going to be turn off and S2 is going to be turn on. What I am saying, S2 is going to be turn off, okay, and S2 is going to be turn on. So in this circuit I wanted to say that my S1 is going to be turn off, okay. So initially what is happen, basically S1 is on, right, and S2 is off. This is very simple thing, like my S1 is on, S2 is off initially. So what is happen, voltage across the capacitor 1, which was, if my switch is on, voltage across the capacitor C1 is 0 because this is a short circuit case, right? And voltage across the capacitor C2 is Vn. So how the polarity of the voltage, so it should be like this, it is a plus, it is a minus, it is a plus, it is a minus. Okay, so this is the polarity of the voltages across the capacitance of these switches. Now why I am interested to know the value of the capacitance voltage, because this is going to be play a very important role in the soft switching. So initially, what is the operation of circuit? So my current is start flowing and it will flow through this particular path, okay, and it will complete its path. So this is how the current flows, right? You know, initially this is how the path of the current. So current is actually flowing through the switch S1. So diode D2 is not basically allow any current to flow. Diode D2, diode D1, they are not conducting. S2 is off by default, so basically it is not at all conducting. So it is open circuit, right? So it is open circuit. So if it is open circuit, so some voltage will happen across it. So where that particular voltage is stored, so that is stored across this capacitor C2. And what is this C2? Drain to source capacitance of this switch S2. Okay, so till this point I hope so initially what is going to be happen we understood. Now comes to the dead time. What is the dead time? We understood that basically to avoid the short circuit of these two particular switches, if these two are short circuit, my supply will be shorted, and that we don't want in any powered electronics converter. So we are going to provide some dead time. So during the dead time, what is happen? During the dead time, basically my both the switches are off for very short duration. Okay, so now initially my S2 is off. Now what is happen going to be a dead time? My S1 is also going to be, I am going to turn off. So now whatever gate pulse I am initially applying to the S1, that is also I have removed. Now S1 is off, S2 is off. What will happen? So one thing is I0 will not change its direction of the current to flow. So I0 can't change its direction suddenly. So it will try to have the same path which is available with this. So it will try to flow like this only. It will not going to change its path. Second thing, now this capacitor come into the play, into the picture. Now initially this capacitor polarity you have to keep it as it is. So it is plus minus. Okay. Now we also know that basically initially this capacitor has some energy stored, which is a V in, and this capacitor C1 has no energy stored, which is 0 volt. Okay. Now during that time what is happen? This capacitor will start basically charging or discharging in the same direction which is available with them. What I am going to say, this capacitor will charging or discharging in the same direction which is available with them. So this capacitor is charged initially, so it will try to discharge. So it will try to discharge at the top. Okay, so it will try to discharge from the negative to positive. It will go up. This capacitor which has the 0 voltage initially, so it will try to charge. So how it will charge? From plus to minus it is going to be charged, and my direction of the current will not going to be changed. Okay, that is for sure. Now just see what is the direction of this current. I will call it as the IC1 current, I will call it the IC2 current. If this direction of the current basically support the direction of the current I0, then this scenario will possible, otherwise it is not possible. What I am saying, if the direction of this current, like this will be flowing in this particular direction, this is going downward, if this direction will support the direction flow of the I0, then this will charge and discharge accordingly, otherwise it will not discharge. So can we see? Okay, so this direction is also supporting, this direction is also supporting. So that means my C2 will start discharging, because initially it has some voltage associated with, now it will start discharging, and C1 will start charging. So my VC1 voltage, what will happen? VC1 voltage will start to build up something, and my VC2 voltage will start to decrease something, because VC2 has the value of V in initially. Now it will start reducing and it will go to the 0, and VC1 has a value of the 0 volt initially. Now it is going to be start charging itself. Okay, so now its voltage is trying to be build up. So far so now I hope so you understood that. Okay, so this capacitor play very important role, and this capacitor are charging and discharging. Now what is going to be happen? Okay, so this process is basically continuing in the dead time. Now further during the dead time only, what is happen? Okay, so this IC1 plus IC2 is 0. The same thing I have also mentioned here as well, because both the current are supporting the direction of the I0. So I0 is nothing but the IC1 plus IC2. Here also IC1 equal to IC2. Now let us say after during the dead time only D2 C2 discharge completely. So if the C2 discharged completely and direction of polarity is again this. So if it is discharged completely, voltage across this is going to be 0, right? And C1 charge completely, and C1 which is trying to charge during the daytime and with this polarity only, it is charged completely. So what is happened? VC1 voltage across the capacitor is now V in, and voltage across the capacitor C2 is 0. Now if the voltage across the capacitor is 0, what is the meaning of this? So it is a shorted. So if it is a shorted, this diode is also going to be short. So D2 start conducting and voltage across the diode T2 is equal to the 0. Now the current direction, you can see that this current direction is there, and how exactly it is flow, it will flow through the diode, okay? And now this is the particular path of the current to flow, because I naught is not going to change its direction. So I naught has created the path through diode D2. As my voltage across the capacitor C2 is basically 0, it is short circuit. That means the diode is also started conducting, and the path to flow the current is this one now. And now you can see that if my diode voltage is also 0, what does it mean to that? If diode voltage is 0, my switch voltage across the switch is also 0. And when the voltage across the switch is going to be 0? When it is switched on. But whether we have applied the gate pulse so far, so now? No, we have not yet applied the gate pulse, even though my switch is turned on and voltage across the switch is basically 0. And hence voltage across the switch is 0, still we have not yet applied the gate pulse to switch 2. So without applying the gate pulse to switch 2, I have my gate voltage, I have my drain to source voltage across the switch is 0. And because of this, when I apply the gate pulse now, when I am going to apply the gate pulse now, already I have the 0 voltage available, and now when I apply the gate pulse, the direction of the current flow is now through my switch. So this is how my direction of the current is now. So current direction we have not changed anything, it will not allow to change. And now going through the D2, it is not going through the D2 as my switch is on. As I have applied the gate pulse, now it will start basically going through my actual switch. Now S1 is off and S2 is on. Voltage across the VAN is again 0, because initially only basically during the dead time only we have make the voltage across the switch 0, and this is how we have achieved the soft switching. So we know that basically how to achieve the soft switching. This is the 0 turn on ZVS of this is my 0 voltage switching of my S2 device, because before only I have make the current voltage to fall 0, and then my current start rising, and this overlap time is very negligible, and because of this 0 voltage switching turn on of the switch S2 we have achieved here. So this is how actually happen in the DAB converter as well. Okay, so there I am not going to explain you basically with the capacitor and all this. Now it's your task to understand. Okay, so this capacitor are there and they are responsible for basically ZVS and ZCS. Okay, how they are discharging, what is the direction of discharge of this, and all those point are very very important. Now what is the important condition we have seen here? What is the necessary condition? So sufficient dead time we should have. Okay, so we entire ZVS happen during the dead time only. So we have provided the dead time, and during the dead time only my voltage across my capacitor is 0, and because of this diode is on, and because of this voltage across the switch is basically 0, and we have make the drain to source voltage 0 even before applying the gate pulse. So all these things we have understood. So that is why the sufficient days time is very important to have the soft switching. Second thing, the energy, half Li square is greater than half C1 V in square plus half C2 V in square. So this will condition mostly happen automatically, because if we have the devices and we already know that the inductor value which we are going to have here, it's sufficiently high value. Okay, and because of this second condition mostly meet, but first condition is really important, to sufficient dead time we need to provide. Okay, otherwise it is not possible to have the basically ZVS of my S2 switch. Now we have seen that ZVS is happening, whether basically same happen for S1 or not, that we are going to see now. Now we will take another case where S2 is going to be turned off. Now initially we have taken that S2 is going to be turned on. Now what I am saying, the S2 is going to be turned off and S1 is going to be on. So now my S1 is going to be turned on. So initially what will happen here, you know that what is initially happen, as my S2 is turned on, S1 is off, S2 is on. Okay, as the S1 is turned off, what is happen? Voltage across this. So this polarity are really important, plus minus. So voltage across this is basically V in, that we also seen during the previous part as well. And voltage across the C2 is what? Again the polarity plays very important role, plus and minus. So voltage across the C2 is 0 because it is a short circuited. Now during this is the first case initially, because S1 is off and S2 is off. Now I have provided the dead time. So during the dead time, what is happen? My both the switches are off. Okay, once my both the switches are off, what is happen? I naught will not going to change its direction. Okay, and this is basically plus and minus. This polarities are really important. Okay, I'm empathizing on this polarity because in this polarity only my basically circuit will operate. Now C1 is charged initially, so it will try to discharge. So how it will discharge? It will discharge in this particular direction. My C2 is going to be charged now because it is initially 0 volt. So it will, how it is charged? So it should charge in this particular direction. So whether it is supporting the direction of current I naught? No, it is not supporting the direction of the current I naught. So this is not possible. So what will happen? What will happen here is that I naught will basically now flow through the diode D2 only, and basically this is the path during the turn off. This is the part during the dead time. So it is not supporting, this I naught is not supported by the charging discharging current of C1 C2. That is why initially I naught is flowing through my switch S2, right? Because S2 is on. Now it don't have any option to flow, so it will try to flow through the diode D2, and during the entire dead time it will circulate here only, and whatever the voltage across the C1 is there, it is still there. It don't have any path to discharge, and this voltage across the capacitor C2 is again 0 volt. It don't have any path to charge itself, and this will happen during the entire dead time. And C1, which is charged initially, tries to discharge but can't because of the direction of the current. And similarly C2 tries to charge itself now, but it will not, it can't basically because of the direction of current. And I naught is again, what is happened? I naught initially flows through the S2, now it will flow through the ID2, and you can see that now here only during the entire dead time it will circulate here. So I naught equal to ID2. Now once the dead time is over, now I will apply the turn on pulse to the S1. So if I will now turn on pulse to the S1, so when I am going to apply the turn on pulse to the S1, whether the voltage across the switch S1 is 0 or not? No, it is not 0. So it will take it some time to have 0, and current will also take some time to go to some higher value. And because of this, again there is a basically this overlapping zone will come, and because of this soft switching is not possible. So what we understood here is that for our buck converter, or for our H-bridge converter, 0 voltage switching is happen for the switch S2, but 0 current switching we have not talked about. Similarly, for switch S1, 0 voltage switching is not possible because the direction of the capacitor charging and discharging is not allowing him to charge and discharge. Okay, and because of this basically S2 has a hard switching, S2 has a soft switching, and S1 has a hard switching. So I hope so you understood till this point. So till this point I hope so you understood everything. Now few more important points you should understand. 0 current switching during the turn off operation is difficult for voltage source fed H-bridge converter, since they do not have the 0 current coming out of that pole, because this is the pole. Okay, and 0 current possibility in such a scenario is really difficult. And because of this in such a H-bridge kind of converter, 0 voltage switching is happen during the turn on, but 0 current switching is not going to be happen. Okay, so in our DAB converter also same sort of the structure is there. So what is going to be happen? 0 voltage switching is going to be happen, but 0 current switching can't be find out there. Similarly, so by adding some external resonating circuit, we can achieve the 0 current switching. Okay, so if we wanted to achieve the 0 current switching, so I need to add some extra element, that is resonating element. 0 current switching is possible without any external circuit during the operation of the circuit. I naught goes to 0 because if it is a DCM operation, so by default my current is going to be 0. If it is a discontinuous conduction mode, you know that what is the discontinuous conduction mode. So my current is going to be 0 before complete half cycle, complete overall cycle, and it will stay for the 0 value for some duration. And if this is the case, then I have the 0 voltage, then I can achieve the 0 current, then I can achieve the 0 current switching, right? But here in this case these things are not going to be possible. So but it is possible if it is a DCM operation, and if I want the zero current switching, then I need to add some extra additional resonating circuit in it. But as far as our half bridge is concerned, we have the zero voltage switching available during the turn on, but zero current switching is not going to be available. And for half bridge also, what we have observed is basically S2 is only having the zero voltage switching, and S1 is don't have the zero voltage switching. But same kind of structure is there in the DAB converter, then how exactly the above switch is also going to be have the zero voltage switching? So we understood that how zero voltage switching happen for basically bottom switch. Even if it is a DAB converter, zero voltage switching happen for bottom switch. Now what about the top switch? So there comes the direction of this current I naught. So we know that the direction of the current is not constant in the DAB converter. It is sometime negative, sometime positive, right? We understood, we know this particular diagram, right? So this diagram is there. So sometime it is negative, sometime is it positive. So the operation of the DAB converter is happen in such a way that when the S1 is going to be turned on, the direction of the current I1 I naught is reverse. Now it is flowing in this direction, but we can see, we will see in the DAB converter that this direction at the time when S1 is going to be on, that time direction of this current I naught is in this direction, and now it is going to support the charging and discharging. And because of this, in DAB converter, S2 and S2, S1 and S2, both the switches in this leg are having the zero voltage switching happen. We will see in the detail, but I hope so you understood the concept, how exactly the soft switching going to happen and all. Okay, direction of current I naught, we know that how exactly it is changing, and that part we also seen in the waveforms, and another time we are going to see in the next video as well. But so far so now the lecture is concerned, I hope so you understood what is a basically hard switching. To remove the hard switching, to get the soft switching, there are the two methods, like basically adding some element into the circuit, like resonating circuit we can add and achieve the soft switching, or another is by the operating principle using the dead time, how we are going to achieve the zero voltage switching. So achieving the zero voltage switching is really possible with the operation of the converter, but achieving the zero current switching turn off is difficult. Okay, so all these point we have covered. So in the next class, what we are going to understand the soft switching in the DAB converter. I hope so this knowledge will be more than enough to by yourself start analyzing how the soft switching happen in the DAB converter, and we will try to understand everything in detail about the soft switching in DAB converter. And next to next video, I have my Plex model available with me. I will show you how the zero voltage switching turn on losses is zero in the DAB converter in the Plex model. Okay, so see you in the next class. Happy learning.